Hello, guys. Nice to see you. I hope you had a great day so far, or whatever the time is for you. And today we're so excited to have our session Ways into Quantum and different stages to go into quantum. And we're so excited to have Anurag Saha Roy from Cruise. I hope I pronounced that correct. How do you pronounce that?
It's all right, yeah.
Yeah, okay.
All right. Hello, everyone. Hopefully, you are all, like Sophia said, having a nice day, morning, evening, night. I'm Anurag. I work at Cruise, and today we will hear a little bit about how I got to working at Cruise and the journey I took to get to this point. So let's start with the screen share, and you should be seeing my slides now. All right. So, firstly, thank you so much to the Girls in Quantum team for having me. I have been following the whole Qvolution and the International Year of Quantum celebrations. Seems like a fantastic thing. So it's really quite a privilege for me to be a part of this. So let's talk about quantum computing middleware. And in the process, I'll also get to tell you about how I got to this point of building an operating system for quantum computers. So first, let's look at a little bit of personal history. I promise it will not be very boring, but we'll get to see some interesting tidbits. So 10 years back, that's when I started my quantum journey. I started working in Bangalore, in India, with Professor Urvashi Sinha. So I started working in foundations of quantum mechanical theory. So very theoretical work, basically underlying the principles of quantum mechanics, underlying the hidden variable theories, and so on and so forth. And then also, how do you verify them experimentally? So you have these theories, and you want to find if the theories are actually practically verifiable, experimentally verifiable. And the way we were doing it back then was through microwave quantum optics. So some of you who have a background in maybe undergraduate physics, you might have done some kind of quantum optics where you work with lasers and with beam splitters and other photonics and optoelectronics components. This is the same, but then instead of laser light, we use microwaves to do this kind of experiment. So this is how I started off. Very, let's say, far from quantum computing, but still, in the quantum technology space. So, but to be honest, I was still very much an engineer who was just masquerading as a physics enthusiast because back in university, so this is during my undergraduate days, back in university, I was actually studying for an electrical engineering degree at one of these technical schools in India. So, very little physics background, very heavy on math and engineering background. I worked on machine learning for signal processing. And for my bachelor's thesis, we created this bionic arm that could use machine learning to classify signals from disabled people. So again, very different from, quantum computing and quantum technologies. So that brings us to the question that if you studied electrical engineering, but you want to work on quantum computing, what do you do? Well, I moved to Singapore. You don't need to move to Singapore. This was back in 2015. Of course, today you don't move to Singapore if you want to work in quantum computing. But maybe to give a bit of context, back then, back in 2015, 16, 17, um, there were two very large institutes in quantum computing. And everybody who was somebody spent some amount of time at these institutes. One was the Institute for Quantum Computing at Waterloo, and the other was the Center for Quantum Technologies in Singapore. So these were, let's say, two different parts of the world, but very large institutions that produced a significant chunk of the quantum computing PhDs every year. So I figured, what better place to, learn quantum and do more quantum than just move there. So I moved to Singapore and started working with Professor Kai Dickman at CQT and then at this startup called Dataminics. And the natural transition when you go from electrical engineering to experimental physics is basically to work on control electronics. So both electronics and control software for physics experiments. And many of you who might have had a physics laboratory course, you might have seen that a lot of experimental quantum optics, experimental quantum physics is essentially just electronics. You can do design, you can do fabrication, you can do embedded software, measurement, testing. So electronics actually plays a lot of very, very important roles in everyday life of an experimental quantum physicist. So that's where I, transitioned into from a background in electrical engineering. Um, one important aspect to talk about here is that also I didn't immediately start with quantum computing, but actually started working with quantum sensing. So quantum sensing is also really cool. Like literally speaking, we use cold atoms, and so I used to work at Atominics, and we build these large quantum sensors. These actually use, let me find a laser pointer. So these trap cold atoms in laser fields by making these electromagnetic traps where you can trap the atoms and then you cool them down, and then you can do interference experiments. Similar to how you would have light interference experiments, you can have matter wave interference experiments, and these can then be used to measure gravity. So you can measure the gravity by using matter waves that are essentially very cooled down atoms. And this lets you do a variety of things. So for example, you can look for minerals under the ground, so without actually doing any digging, any plumbing, anything else, you can just scan on the surface, and that will tell you that, okay, there is a different gravity in this part of the land, and that means there might be some different minerals. Similarly, you use this cold atom-based quantum sensing tools for creating navigation systems. So imagine in the future, if we start living on Mars, where you don't have this network of satellites and you want to create a GPS-free navigation system, or even today in many places where you don't have GPS access, quantum sensing is how you create this kind of GPS-free navigation. So I got to working on this. That is how, let's say, I transitioned into next generation quantum technologies from my background in electrical engineering. But also while at CQT, this is why I think I look back on my time at CQT as one of my most enriching periods in life. It's simply a place with so many different groups of scientists and engineers working on many different things that you learn to do a lot. For example, I got to organize a huge university hackathon on Qiskit back in 2019. And we got a bunch of people from IBM. We had some 100 participants, and I think this was at that time the first university hackathon organized by Qiskit. And this was again only possible because at CQT you had this very nice intersection of quantum algorithm people, quantum hardware people, quantum software people. So just a very nice place with great people who wanted to do cool things. So this was very nice for me because this helped me transition from, let's say, quantum sensing to quantum computing to make this transition by essentially being in the midst of people who did a lot of very interesting and cool things. So let's say learning by osmosis, if that's a thing. Okay, but then now let's say that you want to work at the intersection of machine learning software, electrical engineering, and quantum physics. Because if you might have been, paying attention to what I've been saying, you might have seen that those are the three things that I have some kind of background in. So then, how do you do this, right? So like any good academic, I figured the way to do that is again to move countries because every time you talk to academics, you realize that every 2 years they finish a postdoc and then they're in another country. So of course, but this is all in jest. You don't need to move from one country to another to switch careers. Anyway, so I moved to Germany when I wanted to work at the intersection of these three fields, and the let's say the broad domain of quantum computing or quantum technologies that often works at the junction of machine learning, um, electrical engineering, control theory, and quantum physics is quantum optimal control. So quantum optimal control is the field where you use control theory principles to design operations for quantum computers. I'll have a couple of slides on the technicalities later on. Let's first just look at more pretty pictures. So when I started working on quantum optimal control, we built an open source software library because I really enjoyed working in the open source community. So we developed a software library, we wrote a paper on it, and it was very widely used at that time by a lot of teams that were developing gates and developing instructions for different kinds of quantum computers. And in order to, let's say, learn more on the job, and as you might have seen, I do a lot of learning by osmosis. We organized a seminar series on quantum control. And every week we used to host a speaker from somewhere in the world. This was during the pandemic, so everything was online. And again, I learned a lot about quantum control simply by listening to folks who would come on the seminar series and talk about the kind of cool things that they're doing with these kind of technologies. Okay, so then at the end of 2021, we started Cruise. So Cruise is a startup. At this time, we are 4 years old, 22, 23 people. We are headquartered in Germany, but we have people all over Europe because our team is fully remote. So it's a team that works on developing software for quantum technologies. And this is where I start telling you about the whole, middleware part. But anyway, so it's a software team, which is why we're all fully remote. And we develop this software that works on all kinds of quantum computers and also quantum sensors, superconducting qubits, Rydberg atoms, ion traps, photonics, spin qubits, NV centers. We work with all these different platforms. So that's also very cool and interesting for me because the team that you see here, there are people each coming from a different background of quantum computing technologies, which means anytime we meet, it's always a very, very exciting um, process of learning a lot from others who come from very different backgrounds. And suddenly you find that, okay, a lot of things are similar or a lot of things are different. But this whole, platform agnostic approach of the software that we develop, this also permeates the team that we have, that it's also a team that comes from very, very diverse backgrounds. Okay, so that was enough history. Now let's talk a little bit science, or I think it's more engineering at this point, but who cares? Um, at the beginning of the talk, I mentioned something called middleware. So I said, let's talk about quantum computing middleware today. And I haven't really explained what I mean by quantum computing middleware so far. So let's think about this situation where you have a million qubit quantum computer, right? It's coming next year or something. So we'll all have this million qubit device and everybody will be happy. Either way, next year or 10 years from now, let's take this case of a million qubit quantum computer. And then you have some hacker who's using Shor's algorithm to factor all the RSA encrypted data and steal all your private secrets. So you have these two ends of the spectrum. What you might not have thought about is what happens in between. How does the quantum algorithm, it could be Shor's, could be VQE, could be QAOA, how does it work on the quantum computing hardware? So this is essentially the domain that we're talking about today. So you have the quantum computing hardware on one end, and you have the application software on the other end. What you have in between is the middleware, because it's in the middle, and it's the operating system. So this operating system is very much in line with what you think of as an operating system for classical computers. So, if you have a Windows or a Linux or a Mac, uh, operating system based computer. So there is some hardware. So there is some chip. It could be a chip from Apple. It could be a chip from Intel. It could be a chip from Qualcomm. And then you have, I don't know, Photoshop, or you have some games, or you have Microsoft Word. So that's the application software, and that's the chip. And in between, you have this layer of an operating system, which takes care of a variety of things that are necessary for running these applications on the computer. You need the same thing for a quantum computer. And that's what this does. So this is, let's say, a classical analogy to motivate this. Now, to give you a bit more motivation that comes from the current state of quantum computing. So if you have never worked with a quantum computer, you might not know that quantum computers need to be tuned up very frequently. And this tuning up process is very slow, which is like it's time and effort consuming. But then you might ask, what is tune up? If you have ever worked with one of the cloud quantum computers, so these computers that you access over the cloud from IBM, from AWS, Rigetti, Microsoft, you might have seen that you often get this, notice that the quantum computer is down for maintenance, or the quantum computer is currently not available. So you might have wondered, okay, why is this quantum computer always down for maintenance? Who's maintaining it, and why are they doing such a bad job of maintaining it? This is usually because they are being tuned up. So tuning up means that when you use a quantum computer, you run these algorithms with certain gates on them. These gates need to be designed very carefully after a lot of calibration, after a lot of characterization, to essentially make sure that the microwave signals or the laser pulses, whatever you're using for controlling your quantum computer, they are accurately designed for the application. So this designing the gates and designing how the gates are exactly implemented on the hardware, this takes a lot of time. This is the typical process of tune-up. And unfortunately, quantum computers are not static creatures. They are very dynamic, which means that if you tune up your quantum computer today, that's not enough. It has to be tuned up tomorrow and the day after and the day after. So there is this continuous process of recalibrating your quantum computer, which is why any cloud hosted quantum computer is often down for maintenance. So to give maybe some real life examples, I've been talking in vague terms. This is from a couple of years back. So IBM announced their first 100 qubit plus device back in November 2021. But then it wasn't until March 2022, which is almost 6 months later, that you could actually use the quantum computer in the cloud. And this whole 6 months period is basically how long it would take you to calibrate and design all the gates on that quantum computer. So just having that chip is not enough. You have to actually know how to do your X gate, your controlled NOT gates, and several other gates so that you can get some value out of that device. So how do people tune up a quantum computer? So this is where things start getting a little bit more technical, but bear with me. This is the part that, we talk about science and not just history. So the way to tune up a quantum computer is to run a lot of experiments on it. So that's the first step. You have a chip. Let's say you cool down your this nice golden dilution refrigerator that you see in all the pictures that hosts a chip at the bottom of it. You cool it down. That's why it's a fridge. And then once you cool it down, you run a host of experiments on it. These are experiments like Rabi experiments or Ramsey experiments, things like that. So if you have a physics undergraduate background, those terms might seem familiar to you. And essentially what you're trying to do is that you want to understand that, okay, I fabricated this chip with a lot of qubits on it, but do these qubits actually do what I expected them to do? So you run all this experiment to essentially characterize all the qubits on the chip. And each of these experiments try to find maybe the frequency of a qubit, maybe the amplitude of some pulse, maybe the time that the qubit can be in a coherent state, things like this. And then you fit some very simplified models like an exponential or a sinusoid to that data. So you can see some of this data here. It's a sinusoid or a square pulse or an exponential, things like that. And then you hope that this model is good enough. What you do next is that, okay, so now you have a model of your system, and you have some, parameters that you have learned about the system, so some frequency and other parameters. You can now use this model to do something that we call model-based optimal control. So if there are people on the call who have a background in electrical engineering or control theory, you would identify that optimal control is something that you learn in your control systems course, where you basically have a cost function and you're trying to identify operations or trajectories or instructions that let you minimize the cost function. The same thing here. You want to design a gate for your quantum computer, and your cost function is the fidelity. So you want a very high fidelity, that's the cost function, or a very low infidelity, and you want a very good gate. So you tweak a lot of parameters and you keep changing the parameters until you get good gates. And you do all this on your model that you created from characterizing the system. Once you have done this, what you do next is that, okay, you take this gate, and now is the moment of truth. Let's run this gate on the computer and see if you get a very good C0 gate or a very good X gate or something like that. Usually the results won't be very good. So this is just the reality, that even though you spend quite a bit of time characterizing a system, you will see that, okay, the fidelity is not 99.99 or something like that. So what that means is that your hardware is not exactly what you thought the hardware to be. So you wrote some equations to model the hardware, but turns out those equations are not good enough. So now you again calibrate the gate on the hardware, where you run this kind of calibration processes on the hardware. You run a gate on the hardware, see the result. Okay, it was bad. Run it again with some other parameter, get the result, run it again, keep doing this loop until the infidelity gets very low. So as you might have seen, that this is a very tedious process, which is what I've been talking about, that this is not efficient. So you have designed high fidelity gates, but the question is, how long did it take, right? Because what I described seemed like a very, very involved process. So the answer to how long it takes to calibrate a quantum computer in 2025 depends on the kind of quantum computer that you have. Let's say you have a very simple chip where everything is pretty fixed. You don't have a lot of knobs that you can tweak on that chip. Maybe a couple of weeks to a month, maybe a couple of months at most. But then most of the large qubits, 25 plus qubits, or 25 to anywhere like 100, 500 qubits, we are talking about 6+ months. So that's how long it takes after you get the chip, the square chip that you fabricate, to it being useful for running any algorithms, which means that this is quite a slow process. So question that we can ask to answer this in 2025, like everything else, is how can machine learning help this process? Because as you might have seen that we have a lot of data and we have a model of the system. So clearly we could use the data to learn a model. And that's what we do at Cruise. We create this digital twin of the quantum computer. And again, for the folks on the call who have a background in machine learning, we use something called JAX, which is a library that lets you create differentiable simulations of systems. So we create this differentiable digital twin, we feed it data from the real quantum computing chip, and then use the machine learning algorithms to create a very, very accurate model, which can then be used for getting very accurate gates. And this brings down the process to a few hours from several days, weeks, or months. Okay. So I told you, I gave you some motivation for what is optimal control, why we need optimal control in the last couple of slides. I would just want to touch on the part regarding the operating system. So we talked about middleware. Now let's talk about the bigger picture of what you need to build an operating system for quantum computers. So at the end of the day, what we want to do is we want to have a private quantum cloud. What that means is if you have had some experience working on quantum computing hardware, it is most likely through accessing IBM's quantum cloud, IBM's quantum computing chips in the cloud, or maybe something from AWS, because that's the current way to access quantum computers. In the coming years, as quantum computers grow from laboratory prototypes to production devices, we'll actually have a lot more quantum computers that are owned outside IBM or Google or AWS. So we'll have, your universities will have a quantum computer uh, for people to use as a shared device. And then this will need the same kind of operating system tools that current high performance computers need. So you will need something for managing all the people using the one quantum computer that the university has. You will need some job queuing, some scheduling. You will need to be able to submit gates. You need to be able to work with your favorite IDE, Jupyter Lab, VS Code. You need to know when the quantum computer is up and when is it down for maintenance. So the same things that if you have had a chance to work on your university's high performance computing institute, you will need the same kind of tools for building a quantum cloud for everyone. So this is, let's say what happens when quantum computers get out of IBM and Google to every university and research institute. Okay, so now wrapping up, what did we talk about today? The first thing I want you to take away from the call is that a 10-year BSc-MSc-PhD in quantum physics is not the only path to a career in quantum technologies. I think it's very important because for several decades that has been the case, but that is no longer the case. And also, I want to still sell that quantum sensing is a very, very interesting and exciting field. There's more to computing than more to quantum than just computing. So you should definitely look at that also as a possible field for you to explore as a career choice. And maybe a commentary on the state of affairs right now. So we are at this inflection point where we're going from laboratory devices to production grade devices, which means it is very much an engineering scaling challenge. So we need a lot more people with material science, electrical engineering, computer engineering, embedded systems background, as much as we need physicists right now. And these people will often work in what I would say are the unsexy bits, right? The middleware part of the quantum computing ecosystem, not all the flashy Shor's algorithm and VQE and QAOA or the nice golden dilution refrigerator, but in the middle, which means we'll need people with these kind of background. So if you are from these backgrounds, you are very much in the right place to work in quantum computing.
I was thinking if quantum machine learning could be used or if we still have a long way to apply it. But yeah, thank you.